Physics chapter 18 theory 2 Newton's law of gravitation. Newton used his ideas about mass and gravity to suggest a law of gravitation for 2-point masses. So basically what you need to understand is you have to understand what point masses are. Now Earth can be identified as a point mass in relation to another object, like the moon or the sun or anything, any other object, any other external object. Point in the sense it appears as if it's acting from a single point, like from the center of the earth. Now he considered 2 points masses capital M and simple m separated by a distance r. Each point mass attracts the other with a force F. Right? So this is according to Newton's third law of motion. Every force has an equal but opposite reaction. The point masses interact with each other and therefore extract equal but opposite forces on each other. So exert equal but opposite forces on each other. So maybe you can remember there was a question that you would find in a past paper that deals with specifically this particular part. So the answer can be found in this part itself. A statement of Newton's law of gravitation is shown below. Any 2-point masses attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of their separation. What does that mean? So any 2-point masses, point M, capital M and simple M, they attract each other with force that is directly proportional to the product of their masses. So that means higher is their mass, higher would be the force of attraction. And if the separation, the square of the separation, if higher the square of the separation, lesser would be the force. Right? Note that the law refers to point masses. You can alternatively use the term particles. Things are more complicated if we think about solid bodies which occupy a volume of space. Each particle of one body attracts every particle of the other body, and we would have to add all those forces together to work out the force each body has on the other. Newton was able to show that 2 uniform spheres attract one another with a force which is the same mass if their masses were concentrated at their centers. So that is where it is coming from. That is, Newton established that all the forces work out in such a way that it appears to be acting from the central point. Right? Provided their radii are much smaller than their separation. Right? So, there are some conditions to this. The radii of these objects should be lesser than their separation. Right? If it is not, there are some other factors that come into play. But that is not part of your examination. So, better leave it for your university studies. Then according to Newton's law of gravitation, F is directly proportional to capital M into simple m. So this part. And then it is inversely proportional to 1 upon r squared. Right? So that is it is inversely proportional to the distance squared, or proportional to 1 upon r squared. I hope you understand that. So you combine those two to get an equation. F is proportional to capital M simple m over r squared. And then you take the gravitational constant and make it into an equation. And finally you get the equation F equals G capital M simple m upon over r squared. Right? So if you know the masses of 2 objects and the gravitational constant and the radii, and in this particular situation this r is not the radius of each object, but rather the separation, right? So as you can see here, this part is the separation. This r stands for separation, right? The force is attractive, so F is in the opposite direction to R, right? What does that mean? The force is attractive, so that means it attracts. So it is in the F is in the opposite direction to R. The gravitational constant G is sometimes referred to as the universal gravitational constant because it is believed to have the same value, right? So it is quite easy for us now. G has the same value, 6.67 into 10 to the power minus 11 Newton meter squared per kilogram squared throughout the universe. So this is a universal fact. This is important for our understanding of the history and likely long-term future of the universe. The equation above can also be applied to spherical objects such as the Earth and the Moon, because they will also act as point masses, provided we remember to measure the separation r between the centers of the objects, not from the surface to surface, right? You may also come across the equation in the form F equals G m1 m2 divided by r squared. So obviously m1 and m2 made it simple, refer to two different objects. Let us examine this equation to see why it seems reasonable. First, each of the two masses is important. Your weight, the gravitational force on you, depends on your mass, on the mass of the planet you happen to be standing on. Second, the further away you are from the planet, the weaker is its pull. Twice as far away gives 1/4 of the force. So let's see what that means specifically. Now, your weight, that is the gravitational pull on you, W equals mg. So you know that it would increase if the mass is higher. So it depends on your mass. And because G depends on the mass of the, simple G depends on the mass of the planet you are on, so your weight would depend on both of them. Right? So you understand that. Then further away you are from the planet, weaker will be the pull, this attraction. That is the reason why you can, if you go into the space, you will float rather than falling. Right? Twice as far away gives 1/4 of the force. Why? It is inversely proportional. As you can see here, this F equals 1 upon r squared. Right? So that means if you are here, right, if you are originally here, now let's say this separation, r squared, right? So that is what you need to take, F equals r squared. If you double that, right, if you double the separation, you will get 1/4 because it is being squared, 1 upon r squared. Right, I hope you understood that. Right, then let's, there is a little bit more for us to understand. If the distance is doubled, the lines are spread out over 4 times the surface area, so their concentration is reduced to 1/4. This is the reason. Right? This is called an inverse square law. You may have come across a similar law for radiation such as light or gamma rays spreading out uniformly from a point source. The same scenario happens because it goes and has to act on a larger surface. So when we are talking about large objects, we measure the distance or separation r from the center of mass of one body to the center of mass of the other. Right? So we have to consider as the masses were concentrated at one point, the central point. And also remember, irrespective of their masses, they attract each other with equal and opposite forces, because that is what Newton's third law says. Right? The earth pulls you on with a force, that is your weight, directed towards the center of the earth. You attract the earth with an equal force. That is the reason why you are on the surface rather than getting pushed out or sucked into the center of the earth. Your pull on an object as massive as the earth has little effect on it. The sun's pull on the earth, however, has a very significant effect. Right? So because they are quite large. Right? All right. So let's write down a note. Newton's law of gravitation. When 2 point masses are considered, within brackets, right, with masses capital M and simple m separated by a distance r, each point mass attracts the other with a force F. With a force F. Within brackets, according to Newton's third law of motion. Based on this principle, Newton's law of gravitation is developed, which says use a different colored pen and write down. Any 2 point masses attract each other with a force directly proportional to the product of their masses, and inversely proportional to the square of their separation. Inversely proportional to the square of their separation. Please draw figure 18.5. Pause the video and draw figure 18.5. And after that, I want you to write down these equations as it is. Force is proportional to product of masses, or F is proportional mm, and then these two equations, and after that you develop this, and gravitational constant g, this equation, and then underneath that write g. After you write these things, pause the video, write those things, and then write g is universal throughout, universal, and has a value of 6.67 into 10 to the power minus 11 Newton meter squared per kilogram squared. Right. When taking, leave a line and write, when taking the separation between two large objects such as planets, the distance should be calculated from the centers of their masses. Leave a line, put a star and write down. A person's weight, a person's weight depends on his mass as well as the mass of the planet he is on. Next star. Further away you are from the surface of the planet, lesser would be the attraction on you by the planet. Next point, twice as far away would give 1/4 of the force. Please draw this figure 18.6 also. That might give you an idea as to why it happens like that. I hope you understood. If you understood, please go through the video once or twice, as much as you can. As long as you understand, that's the purpose of this. If you do not understand, listen to it again and also read through the note. If you have any doubts, please raise them. If you have understood, please do question number 1 and 2.